Today we're going to start our next chapter, chapter 23, which is the problems around electrical induction, primarily looking at problems involved with electricity generation, circuits, and technologies. And we will start with actually problem number 1. And in order to give you an introduction to this, the key formula, initial formula here is the following. Psi, PSI, or the is the Greek letter to stand for what's called magnetic flux. Magnetic flux is a change in magnetic field over a specific area times the sine of the angle theta perpendicular to that field, where B represents the magnetic field, A is the area in which the magnetic field is passing, and theta is the angle of the magnetic field to that area. If the, I said sine, I'm sorry, this is cosine. If the angle is 90 degrees, then the cosine of theta is 0, and the magnetic flux in that case is 0. And this is actually what happens with the first problem. It asks the following: what is the value of the magnetic flux at coil 2 in figure 2356, which is right below the problem, due to coil 1? And you look at those two coils and they're at right angles to each other. And because they're at right angles to each other, then it's cosine of 90 degrees because they're at right angles to each other, and therefore, which is 0. And so the magnetic flux in that case is going to be 0. Problem number 2 is exactly the same. It states the following: what is the value of the magnetic flux through the coil in figure 2356B, which is on the right, due to the wire? Again, these two are in right angles to each other, and therefore the answer to number 2 is also 0. Problem number 10. Now, problem number 10 moves into a new section. No, I'm sorry, it doesn't move into a new section. The next group moves into a new section. Problem number 10 says the following: referring to the situation in the previous problem, which was an MRI technician moving his hand in a region of a very low magnetic field strength in an MRI scanner with 2 Tesla field and his fingers pointing in the direction of the field, find the average electromagnetic force induced in the wetting ring given the diameter of the ring is 2.2 centimeters, and assuming that it takes 0.25 seconds to move it through the field. So it's asking the question, what is the current induced in the ring if the resistance is 0.01 ohms? Well, in order to do this problem, you have to first calculate the EMF. So the EMF is equal to the number of turns times the change in flux over in a area over time, change in time. N is equal to the number of terms. In this problem, the number of terms is 1. The change in flux is delta psi, and the change in time is 0.25 seconds. So we can put that in 0.25 seconds. So what we have to find is delta psi. Now psi is equal to BA cosine of theta. Theta in this case is 0. Therefore, the cosine is 1. And in order to calculate the change in flux, we put in delta theta is equal to B, which is 2 Tesla, times the area, which is pi times the radius squared. This diameter was 2.2 centimeters, so this is 0.11 meters squared. And if you calculate this out, E, if you put this in for the delta flux and put that up here, 1 here and 0.25 here, this is actually not part of this problem. You end up with an EMF of 2.04 millivolts. Okay, or 2.04 times 10 to the minus 3 volts. Now it tells you, in A, it tells you that the resistance is 0.01, so what is the current? Well, the current is equal to the voltage divided by the resistance, which is equal to 2.04 times 10 to the minus 3 divided by 0.01, which is 2.04 times 10 to the minus 1 amps. I wrote that down wrong. Sorry about that. Okay, so the second question in number 10 is, what average power is dissipated? So P is equal to I squared times R, or V times R. In this case, so 3.04 times 10 to the minus 1 squared times 0.01. And if you do the math here, you get 9.24 times 10 to the minus 4 watts, or 0.924 milliwatts. And C, the question is, what magnetic field is induced at the center of the ring? Okay, so the field in the center of the ring from the last chapter is equal to mu 0 times I over 2r, where r is the radius. So mu 0 is a constant. It's equal to 4.4 pi, times 10 to the minus 7 times I, which is 0.304, divided by 2 times 0.011, which is equal to 1.74 times 10 to the minus 5 Tesla. And that's so that's the induced field. And what is the direction of the induced field? It's going to be counterclockwise, given the setup that's described in the previous problem. Okay, so let's move on to number 12. Number 12 states, a 0.25 radius, 500 turn coil is rotated 1/4 of a revolution in 0.17 milliseconds, originally having its plane perpendicular to a uniform magnetic field. This is equivalent to 60 revolutions per second. Find the magnetic field strength needed to induce an average EMF of 10,000 volts. Okay, so E is equal to delta psi over delta t. And so this is going to the delta psi is equal to B times the change in area times the number of turns that occur. And delta t stays the same. Now if we rearrange this in order to solve for B, we get E delta t over delta A over N. And so that's going to equal 10,000 times 0. Well, let's do it this way. 4.17 times 10 to the minus 3 divided by 0.196, which is the area that I calculated out looking at using the radius of 0.25 times squared times pi, and the number of turns, which is 500. And if you do that, you get a field of 2.425 Tesla. Number 14. Now we're going to come back to this problem in a future problem, so I just point that out. E, so number 14 states, a lightning bolt produces a rapidly varying magnetic field. If the bolt strikes the earth vertically and acts like a current in a long straight wire, it will induce a voltage in a loop aligned like figure 2357b, which is on the same page there, the image on the right. What voltage is induced in a 1 meter diameter loop 50 meters from a 2 times 10 to the 6th amp lightning strike if the current falls to 0 in 0.25 or 2.25 microseconds? So again, the E is equal to N times delta psi over delta t. And psi is equal to B times A, and which is equal to pi r squared times B. So we can put this in and say that delta psi is equal to delta B times pi r squared. Because the B varies, in the problem it says that the B varies over time. So B is equal to mu 0 times I over 2 pi d, where d is the distance from the loop. So delta B, what varies is the amperage. It dissipates when a lightning bolt strikes. And so if we put this in here, then we can say that E is equal to mu 0 delta I over 2 pi d times pi r squared n, and put delta t on the bottom here. Got to have delta t in here. Which equals mu 0 n r squared delta I over 2d delta t. The pi's cancel out. And if you put numbers in here, you have 4 pi times 10 to the minus 7. That's mu 0. The number of turns is 1. R is 0.5 squared. And then the I is minus 2.0 times 10 to the 6th. And so that's the change in amperage over time. 2 times, it's 50 meters away, times 2.5 times 10 to the minus 6. That's delta T. 10 to the minus 5, excuse me. And so that equals 251 volts. So that's number 14.